I'd like to start this video by giving another key example that's going to come up again and again throughout 206A. And that is the example of dihedral groups. So these are the focus of section 1.2 in Dummett and Foote. And that section is going to go through what I'm going to say in a little more detail. So please read that. So what is a dihedral group? So we pick an integer n that's at least 3. And we're going to define d2n to be the group of symmetries of a regular n-gon. So this is easiest to see with an example. So like when n equals 4, d8 is the symmetries of a regular square. So what does that look like? Well, there are 4 rotations where you take the square, you rotate it 90 degrees, 180 degrees, 270 degrees, or 0 degrees. And every vertex gets sent to another vertex. But in addition to these 4 rotations, there are also 4 reflections. So you could take this vertical line and flip. 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1. Or you could flip on the horizontal line, or you could reflect over either of these 2 diagonal lines. So what is this definition really? The group of symmetries of a regular n-gon, that's a little vague. It's a nice informal definition to keep in mind. But these symmetries are really rigid motions of a regular n-gon. But what does that mean? So you can pick up your square, you can move it around in 3-dimensional space, like you can rotate it over like this, and then you put it back down on top of your original square, and now the vertices have moved around. The one that was originally labeled 1 maybe is over here now. The one originally labeled 2 maybe is over here now. So this rigid motions is a nice way to understand what kind of symmetries we're talking about. And then what I think about when I think about the dihedral group is that the elements are actually permutations of the vertices. So you label your vertices 1 to n, and you permute them. And there are just some rules about how these permutations work that come from the fact that these are rigid motions. So if you take vertex 1 and you send it to position I, then because 2 is next to 1, that means wherever you send 1, 2 needs to be next to that. So if you send 1 to I, then 2 either gets sent to I minus 1 or I plus 1. And in this way, you can see the order of d2n is 2n. Why is that? Because there are n choices for where you send the vertex 1. And then once you've made a choice, there are 2 places left that you could send 2. But once you send 1 somewhere and you choose an option for 2, everything else is fixed. So for a lot more about dihedral groups, I recommend that you check out section 1.2. But this is enough to give you a flavor of how this geometric description leads to a set of permutations on your labeled vertices. Not all the permutations, but a special subset of them that come from rigid motions. So I'll pause and erase, and then I'll talk more about groups of symmetries. I next want to talk about a really important example, the example of symmetric groups. So these groups are the focus of section 1.3 of Dummett and Foote, and that's going to go into more detail than I will here. We'll come back and say much more about permutation groups and symmetric groups later on, so I'll be brief. What's the idea? So you take a set. It can be a finite set. It can be an infinite set, whatever. Just take a set, and you take the set of all bijections from that set to itself. The most important case, the one that we're going to focus on again and again throughout this course, is the case of omega equals the set of numbers from 1 to n. So we're going to write Sn for this set of all bijections from 1 up to n to itself, or the set of all permutations of these n elements. Sn is a group under composition. What does that mean, composition? You first do one bijection, and then you do the next one. So it's just composition of functions. So that means you get associativity for free. There's the identity permutation, where you don't change any element. You send 1 to 1, 2 to 2, 3 to 3. And every element has an inverse. If you have a bijection that sends I to sigma I, the inverse permutation just takes sigma I and sends it back to I. You just undo all the permuting you did. Okay, so how do we write down a permutation? Well, one thing you can do is this two-line notation where you take 1, 2, 3 up to n, and just below it you write sigma 1. Where does 1 go? Sigma 2. Where does 2 go? Up to sigma n. Where does n go? So what is this second line? It's the numbers 1 up to n in some permuted order. So the top line is always going to be 1 up to n, so it doesn't actually give you any information at all. So one-line notation is you just write the second line. You don't write the first line at all. You just write sigma 1, sigma 2 up to sigma n. But the most common and the most useful for us is going to be cycle notation. So what's the idea of a cycle? You have the element 1. It goes to sigma 1. Maybe sigma 1 is 1. So you start at 1, you end at 1. That's the cycle. 1 goes to itself. But if sigma 1 is not 1, then you can apply sigma again and say, where does sigma 1 go? It goes to sigma of 1. Maybe that's 1, and now it goes 1, sigma 1, 1, sigma 1. It's a cycle of size 2. You just go around and around and around. But maybe it goes somewhere else, and then maybe it goes somewhere else, and maybe it goes somewhere else when you apply sigma again and again. But since the set from 1 up to n is finite, if you keep applying this sigma to the next element, the next element, the next element, you eventually have to come back to an element you've already seen. And because sigma is a bijection, you can show that the first element that you see that you've already seen must be 1. If it were something else, then you'd have two different elements mapping into the same thing, and you wouldn't have a bijection. So you can read the details of that in section 1.3. Dummett and Foote writes about the cycle decomposition algorithm. So this is a good example of the kind of thing that is pretty straightforward, and we're not going to do all of the details of this in lecture, but you'll get a lot of practice in the homework and in discussion when you solve problems about symmetric groups.